Welcome to the second meeting for the common language of the proposal called Magnetic Agnostic Structure. Well, you all know me, I'm Alfonso. I'm going to go over what we are going to talk today, but stop at any point with you. The point of this that this is a discussion. Just stop me and ask whenever you feel like, okay? We are going to start just going over what we talked on the first meeting. Quickly, like I introduced the future problem that we are going to have about the lack of engineers, actually the lack of labor force in general, and how the electronics market will go up, and especially magnetics, which is the top graph, and the labor force is the one below. So we need some solution to automate repetitive tasks. We need to improve the communication. We need to improve how we make decisions. And for that, the first step is to have a common language between the software, the designers of the software for electronics, the designers of magnetics, and the manufacturers. And we really have to admit it. Finally, Excel has reached its point. It's not, if it ever was a good software, it's not anymore. But we also talk about the necessity of the rules or the requirements that such a common language for magnetics must have. It has to be open and ambiguous, so it doesn't matter who interprets it as software, a machine, a human. It has to be the same, has to be versionable, has to be scalable, has to have some rules. And we also went over how to discuss a magnetic core with this language proposal. Okay, in this one, I'm not going to continue with magnetics. I'm going to continue with the inputs actually, which is what I call inputs. Okay, and what I call inputs? It's everything that describes how a magnetic has to be, and so all the requirements, the citations, the operation conditions, everything that is there. And I'm going to explain why we need to define the input without any ambiguity to be able to define properly a magnetic. We as humans always try to classify things to when we struggle to understand the world around us. We have, for example, the samples of the animals and the plants and the living beings. We might say that a dolphin is a mammal, I don't know how it's in English, because it has lungs and because it gives birth. We might say that a tomato is a fruit because it has seeds. It's from a plant that is the part that is around the seeds, designed to have those seeds around. And some classifications are science-based, but then some people come and say, no, the tomato is not a fruit, it's a vegetable because I put it on my salad. Most people consider a tomato a vegetable, actually. So I call this salad-based classifications. And we also have them in power electronics and in magnetics. We have science-based classifications. We might say that an inductor is an inductor because it stores energy, and a transformer, instead, what it does is transfer energy from the primary to the secondary instantaneously, or that a choke is designed to lose energy at certain frequencies, so it filters the signals at those frequencies. And then there are some other rules or common knowledge that is not so much based on science. We have heard a lot. A flyback has a primary and a secondary, so it's a transformer. We would say that, okay, we always have to use the triple insulated wire for flybacks. Maybe not. Maybe we can use double insulated. Maybe use some other kind of insulation to comply with the standard. Or we say that we should always make the core and when it loss is equal, so they have the same bats to have an optimal design. I'm going to meet you just because I'm
yeah, please.
Yeah. So I'm not against rule of thumbs that in general, as I said, they are not based on science. I say they are salad-based too. And I say this because some people might argue that these rules help us design magnetics faster. And maybe they do, but they are going to mediocre magnetics. My opinion is that they actually are inhibiting, preventing us from really understanding how the electromagnetic field work, how the magnetics really behave, and to actually preventing us from designing better magnetics. And the reason for this is, this is because normally when people use these rules, they don't think further than those rules. They just apply them and continue. And this is the same like putting a totally different example. When you see a lightning in the sky, you might say, okay, this is due to the static charges in the clouds, or you might say, no, this is Thor moving his hammer around and provoking these thunders and lightning. And both are different ways of explaining the same effect that we see in nature, but one take us to more knowledge, to science, and another one is that then for knowledge. Or maybe then for knowledge, but or maybe it will just take us to Ragnarok. But it's not the proper way of doing science. At least, this is my opinion. Feel free to add me and say otherwise. If not, I will continue. So, and I say all these classifications because even when they are science-based, the magnetic classifications, we need the excitations. Like a magnetic component without the excitation is just a piece of ferrite, of iron, with some copper wires around it. Is the excitation what makes a magnetic good for an application? And with that excitation, different excitations, the same physical component can work for two different applications. Like, for example, if we had a ferrite with a gap and two windings, that can be perfectly a LLC transformer when we are using the leakage inductance for the resonance inductor, or it can also be a really cheap flyback. Or for example, if we have a transformer, a CMC with these two windings, that CMC under different configuration, different excitation, can be a transformer. And the only difference would be that in one case, in the CMC, we are interested in losing energy at some frequencies, in order to filter those and transfer that energy to the core as heating. And in the transformer, we are more looking at efficiency, at coupling, at other requirements. And I know this is simplifying a lot, and that there are more requirements in magnetics, in transforming inductors, common mode chokes. There's a lot. You can see here what the PSMA did for all the requirements in magnetic. But this is actually reinforcing my point. Like, all these requirements is what really makes magnetic. Like, they define the goodness of a physical component that's just made of iron and wires for a given application. They actually make our magnetic components. Without this, they are just pieces of hardware without any actual application or goodness. And all these things is the reason. But this is, I hope I more or less explain. This is why I think that the requirements, that the inputs, the citations must always count the magnetic, and they are fundamental to how magnetic is defined and how it's described, especially if we want to have it without ambiguity, like it's the objective of this common language. So now comes the part where I will show you the proposal that I have for defining these specifications. I will start going back to what we saw in the previous meeting, the starting point. This is what I call the mass file. This is the topmost file in the standard, or in the language, and it's composed of three components: the inputs, the magnetic, and the outputs. The magnetic is what we talked in the last meeting. It's the physical component, and it's composed of the core, the coil, and some information about the distributors and the manufacturers. And actually, I would like to make a little stop here, because one of the results of the previous meeting that there was a proposal for changing the name of winding to coil, because then that would prevent from having ambiguity with the individual windings. And also some people say that not only the core, magnetic cores or the wires might have a distributor or a manufacturer information, but also the magnetic. So that's some positive things that already came from these all these findings of mine. So in this, so we also have the inputs, is what we are to talk here. We have been talking already about the requirements and operation points. And then we have the outputs that we will discuss in some future meeting. And they are basically the combination of combining the results of combining one input with one magnetic. So, and that can be there due to a modeling, analytical simulation, a measurement. All this is covered by this language. Okay. If we take a look at the inputs, as I said, stop me if you have any question, if something is not clear. This is the how an input is defined. It's separated into two fields: the design requirements and the operation points. The requirements, everything that has to do with where the magnet is going to be, how it must behave, and then the operation points are a list of excitations the magnetic has to comply with, has to work in those points. And I know that the most common way of doing these things right now is by ranges. People come and say, I want a magnetic that works from 5 volts to 12 volts, 1 ampere to 5 amperes, and 100 kilohertz to 300 kilohertz. But then, how do we combine those? I mean, we have some knowledge of the topology. We might guess that the highest voltage goes with the lowest current, but what about the frequency? There is not clear. And then if we also add some temperature ranges, if we add some duty cycle ranges, then it's totally ambiguous. It totally depends of the mind of the interpretation of the user, how those points, how those ranges define a magnetic. And this is what we want to remove with this common language, ambiguity. Because, and then what I propose is to have a list of operation points clearly defined, like 1 ampere, 12 volts, 100 kilohertz, 5 volts, or 5 volts, I don't know, the other combination, 5 volts, 5 amps, 300 kilohertz, doesn't matter. It's all clearly defined. It's all points of the working spectrum that the magnetic has to comply with. And the user, what the customer can do is find the worst cases for this. If we take a look at we'll talk about the operation points later. Taking a look at the design requirements, we can see the usual suspects for any inductive component, of course, magnetizing inductance and the turn ratio, but we can also see the insulation requirements, everything we need to calculate, the creepage, the clearance, the interlayer insulation, the typical thing from the standards, the pollution degree, the insulation type, the voltage category. We can also define the maximum temperature that our magnetic must support, withstand, the maximum dimensions, maximum weight, the market that is going to work with, the topology. But even if there are many, at the end of the day, the only two that are really, really compulsory are the magnetizing inductance and the turn ratio. And we are going to take a look at one example here. This is the basic design requirements. This is the way to define it. And on the right side is is a mass file with every design requirement that we might have in magnetic. Okay? Two little details I wanted to comment here. If you see things like the temperature, the capacitance, the leakage, they are not values. They are what I call is a dimension with a tolerance, which if we go here and it's defined here, is just a field that has basically the nominal value, but it also has the minimum and the maximum, and this allows us to register here any data that we might have, like any requirement we might have, even the minimum. Typically, we have the minimum magnetizing inductance for transformers. We might have a maximum inductance. We might have a nominal turn ratio, but then we might allow some wiggle there. So we can define also the minimum and the maximum for the turn ratios. And the same with all the fields that are defined as kind of dimensions with tolerance. Another thing is that the turn ratios the fields like the turn ratios or the leakage inductance are list of relationships to the primary. So they are not basically they are list with not one component per winding, but one like the number of windings minus one, because everything is referred to the primary. Okay. So for example, in the example on the left, the turn ratio is an empty list. That means that there's only one winding, the primary, and the primary cannot be referred to itself. So we don't put it in the example on the right. We see that the turn ratio has a nominal value of 4. That means that there's just one winding secondary that has a turn ratio of 4. But there are two windings, even if there's one element. If we have 3 windings, then there will be 2 elements in the turn ratios. Okay. If we continue and take a look at the operation point, I decided to put some fields here, not on the other side, like the temperature or the cooling, to allow the chance of for the designer, for the specification writer, to specify different cooling operations, different ambient temperatures for different operation points, because we might have cases where a certain load, the rest of the components are creating a higher temperature in the ambient that they will be at a smaller load. So this is just some freedom for the user to find these operation points. And then typically the cooling, we might also define, we can have natural convection, for convection, heat sink, or cool plates. And everything that you have there is able to define it. It's what you need to define these conditions. And then the other side is the operation point excitation. This is a list of excitations, one per winding. Okay, if we have only one primary, then we only need one excitation. If we have primary and secondary, we need minimum the excitation for the primary, and we can derive it with the turn ratios. But ideally, we need everything for every winding to be properly defined. If we take a look at the excitation, I decided to have all these fields like current, voltage, magnetic field strength, magnetic flux density, magnetic current, which is every signal that is based on time that happens inside the magnetic component. They are all time-based, then the frequency is something that is shared among all of them. We cannot have a current and a voltage in the same winding with different frequencies, okay? And then all the frequencies is a number, the kilohertz that we are running. Actually, is in every, I didn't say, I said it in the previous meeting, every unit that you hear is based on the international system without any base units like hertz, amperes, and watts and volts and everything. If we take a look at this electromagnetic parameter, it's not the best name ever. If some of you has any proposal how to name some parameter that is used for defining current voltages, flux densities, whatever, please contact me and send me your proposal, because I'm not really happy with the name. But okay, for now they call it electromagnetic parameters, and it's used, as I said, to find any signal in the magnetic. As happens in other fields in the magnetic, in standard, there can be there have some fields that are complementary, that are different ways of describing the same thing. Just give me a moment. Like there are different descriptions. Like for example, in this case, for the electromagnetic parameter, we might define it as a waveform, as a series of points. We either with existing sample points or with time. We will see it more in the example. But we can also define a current by its harmonics, that we obtain by applying the Fourier transform. But we might also define it as we normally humans do, like with the duty cycle, the peak, the offset it has, even the shape, the label that we put, we classify. We were talking about classifications, how we classify the signal. We call it this triangular, sinusoidal, rectangular, whatever. And all these different descriptions. They are complementary between each other, and we can, from one, we can extract the others, more or less. With some lost at some point, as you all know, the harmonics, the Fourier transform must have an infinite number of harmonics, but we cannot have an infinite numbers in softwares. So something is always lost. If we take a look at some examples, what I did, what I'm going to show you is the same excitation, current and voltage, described by 4 different ways with these descriptions that I show. The first one is the waveform with equidistant points. It's typical ones that you get from SPICE. Basically, it's a list of floats, of doubles, of numbers. When all of them are sampled at different at a given frequency, and if you tangle one after each other, you will get the shape, the waveform. This is not really efficient for this waveform. This is using more than 8 kilobytes. We'll see why. And this is important because this language is thought also for software, for training, for having big data for magnetics. It needs to be efficient. We need to store things as efficient as we can. We will compare it with the other formats. So for this one is 8 kilobytes, and we can see here the name, the frequency, and the current, the waveform, and the voltage waveform. If we go to also the waveform, but what I call the compressed format, where we are just storing the points where the slope changes, in this case, it's much smaller, it's half a kilobyte. And here you can see how we are just storing these points that we see here. But we also need to store the time inside the period where these points are in order not to lose information, because now they are not equidistant. Okay, and we might also store some ancillary labels for helping us understanding what it is, but it's not. I call it ancillary because it's not really needed, but it's helpful. If we go to the next way of describing this is the typical one. You define this as a peak-to-peak. There's a 4 pairs. This is 0.42 with an offset of 10, RMS, effective frequency. Those are more processed data. Everything is just used to define how this waveform is, and it's just triangular waveform. The same with square or the rectangular for the voltage. This is also a bit bigger than the previous one, but also quite efficient. And then we have the least, or not least efficient, but it's also quite big. It's the one harmonics one. We can see here a list of amplitudes, a list of frequencies of each of the harmonics that define these two waveforms. This is really big. It cannot fit in the screen. That's why it continues, but you can get an idea of how it goes also for the voltage. And I didn't want to finish this because the reason why I have 4 things in my excitations: the current, the voltage, the magnetic flux density. Not all of them are compulsory. They are all optional, and sometimes one of them is more comfortable than the other. And this is one example. When we are working, this is just a data point from the data done by Magnet from the University of Princeton and Dartmouth, where they have a huge database of core losses points. In this case, we are not interested in the current or the voltage, because that would imply also describing how the setup is. We don't really want, because for the losses, we only are interested in the magnetic flux density. So that's why for the excitation, we might also define the magnetic flux density and that. And this is how you store one data point for core losses. You just define the magnetic flux density with the frequency, the peak, and there's one question that I will answer later. The duty cycle, and then apart from that, we just need to store the temperature and the value of the volumetric losses. And if we want to store the origin, it's also nice. This is how we store the data points, the core losses data points into the Open Magnetics database. Okay. And after all this ranting, complaining about the requirements and the data structures, you might be thinking, do I really need this? Because I have been working all my life just sending to the customers an Excel file, a Microsoft Word file, and then the customer fills it up and sends it back to me. But I ask you, how many times that procedure has ended up with misunderstandings, with many exchanges between your customer or your manufacturer and you have emails, meetings, just to clarify points that are not clear in those, because different people, different engineers understand things differently. Okay, so this is one of the advantages of using MAS. This is one of the things I want to achieve with a common language. When a customer defines, or a designer defines a requirement or a magnetic, is unambiguous. Anybody that follows the rules is able to understand that those requirements, that magnetic, without any room to interpretation. And that saves a lot of time. That makes us more efficient. And we are going to need that efficiency in the coming years if we want, as we discussed at the beginning, okay? Also, now it's really, now there's some talks getting trendy to like talking about how we can not only simulate magnetics, not only model them, simulate them, but also have a software that is able to create a magnetic, to suggest a magnetic, to synthesize a magnetic. And we might be far away from it, yet of the perfect magnetic, but I think that a software, it's possible to create nowadays a software without artificial intelligence, just with the knowledge that we have, the model, because at the end of the day, that with the knowledge that the normal engineers use in their everyday, we can create a software that is able to suggest, to synthesize magnetics up to, like, that they are not the perfect ones, but they are good enough to work. And then that's where the human can still come and improve them. And in order to have these synthesizable magnetics, we need to perfectly define the requirements, because a human can understand, can assume things, but a machine cannot. It has to be, everything has to be unambiguous. And if we look more to the future and we really want to have artificial intelligence, we need to create a database of points, a database of magnetic designs, and those magnetic designs, they must have also inputs, so we can train an artificial intelligence with it. And for that, as I said in the previous meeting, we need a common language, a way of storing this data commonly between us. So then the data engineers don't have to go crazy cleaning and processing the data from each different company. This is more everything I wanted to discuss today. I don't know if you have any question before I talk over the next step, or you prefer that I go and we discuss later. But if you want, unmute and ask it as you want. If the slide will be available, yes. Hopefully this time the recording will be available too. Sorry for the last time. I don't know what I touched and it broke. But also the recording, the slides and the recording and the transcription will be available after this meeting. And okay, so if there are no questions for now, I would like to talk a bit about the next steps. For the next meeting, I would like to discuss the wires and the coil, how to unambiguously define a wire. Doesn't matter if it's rectangular, round, solid, leech wire, planar, a PCB, doesn't matter. It can be described. And also the same with the coils. Ideally, it will be in September, when we have all enjoyed the summer, the holidays. If we survive this heat wave, I hope, if some of you are in the Mediterranean countries, I hope you have AC machines. But I think September will be a good date. Also, we have a community. It's growing little by little. We have some discussions about magnetics. We share some content, some papers, some events, some jokes. It's free. The only thing that you have to do is register by Discord, but it's also free. And it's a really good software, and it's really comfortable to use. And we can have threads and everything for discussing this, which is perfect for discussing these ideas. And finally, I'm planning to do an online form, like a web page with everything that we have talked here today and that we discuss in the coming days about how to create these design requirements and the operation points is in a friendly way. So I want to create a website that where the user can enter the requirements for the magnetic, and they can download it either in the mass file or in a PDF version. And basically, I would need some beta testers, some people to check it, tell me if it works, what would be improbable. So if any of you want to volunteer, I would be really thankful and offer PR in payment when you come to Madrid. And I would like to, before finished, to do some advertisement or publicity spot for Open Magnetics, which is the broader project of this one, which is an open source, free, and web-based tool set for magnetics. Is everything that we discussed in the previous meeting and in this one is implemented there. You can go and play with the magnetic cores. You can, for that, what we talk here, not the design requirements that I'm going to do, but everything about the waveforms. You can go there. You can customize the waveforms with inserting the points and the times, with the templates. You can even drag around the points and draw your own waveforms, and you will get immediately the Fourier transforms and all the peak, the efficient frequency, the effective frequency, the total harmonic distortion, everything that you might need for your calculations. As I said, it's free to use. You don't even need to register. Really, we don't want your data. Just go use it and you tell us what you think about it. That's everything for today. Thank you for listening. And even greater thanks to all who helped me prepare this. And if you have any question,